So we are going to start chapter 2.2 by explaining the very simple concept of a matrix inverse. It's very simple, but it's also very, very important. So, what does it mean? Up to now, we have been doing the following. We had a vector x, and we applied a linear transformation, or we multiplied vector x by a matrix A, such that we obtained a vector v equals A times x. That was up to now, yeah? But now the question is, can we go back from v to x by applying another linear transformation? In other words, can we start with v and then go back through some transformation that gives us x? And the answer to this question is that sometimes this is possible to do, and this transformation is called the inverse transformation, and it is denoted with a -1 as a superscript. Okay? And what does this inverse transformation mean? So it means that x equals the inverse matrix multiplied by vector v. Okay? So compare these two cases. We have v equals A times x, and then we have x equals A minus 1 times b. That's the concept of inverse transformation. What is the formal definition of an inverse transformation? Well, to define it, imagine we do the following chain of things. So we start with x, we now apply matrix transformation A, and next we apply matrix transformation A minus 1. What do we end up with? Of course, we end up with x, right? Because we apply a transformation and then we do the inverse. So we are undoing the transformation. But what does this mean? We can write an equation for this, right? So this means that x is equal to this chain of matrices applied to x, yeah? So we start with vector x, we multiply matrix A first, and then we multiply matrix A to the -1 second. So we can write this equation here. But of course, x equals x, which means that this transformation here, which is the total transformation, is actually a transformation that does nothing. This is the identity matrix I, which is ones in the main diagonal, yeah, and zeros everywhere else. So this total transformation is equal to the identity matrix. So this means that A to the -1, so the inverse of A times A, is equal to the identity matrix. And the order doesn't matter, because you can also do first the inverse and then the transformation A, and you still get to the same place, because one transformation is the inverse of the other. Therefore, you can write that the inverse of A times A equals A times the inverse of A equals the identity matrix. And that's the definition of the inverse. Let's see two examples. For example, imagine you have a transformation as follows. This transformation scales everything along the x direction by 3, by a factor of 3, and it scales everything in the y direction by a factor of 1/2, right? So, for example, if we have this xy plane and we have a vector v here, so the x component we multiply it by 3, so we end up here, but the y component we divide it by half. So instead of this, we end up with half of it. So we end up here. So this would be our endpoint. This would be A times B. So what would the inverse transformation do? The inverse transformation would be a transformation which squishes or scales the x direction by 1/3 to compensate for the stretch, and then it scales the y direction by 2 to compensate for the 1/2. Yeah. Therefore, the inverse transformation which will be a matrix A to the minus 1 must scale the x direction by 1/3 and scale the y direction by 2. Therefore, the inverse must be equal to this matrix: 1/3, 0, 0, 2. And that is the inverse matrix. Okay? You can check that A times A inverse equals A inverse times A equals the identity matrix. You can do those matrix multiplications yourself. Okay, another very simple example. Consider the rotation. So consider a transformation as follows. So this transformation rotates all vectors by theta degrees anticlockwise. Okay? And you remember that we found this transformation in a previous problem, and it's the following. So, for example, in this case, if we have a vector v, we just rotate it by a certain amount, and this amount is equal to the angle theta, and this will be A times b. Okay? So what will the inverse transformation be? Well, if this transformation rotates by an amount theta anticlockwise, then the inverse transformation must rotate a space by an amount theta, but clockwise. Yeah? So inverse transformation must rotate vectors by theta clockwise, which in our notation, when we said theta would be negative if we are rotating clockwise, so we rotate by minus theta anticlockwise. Therefore, the inverse matrix, we simply have to substitute a rotation angle of minus theta. So the cosine, being an even function, stays the same, while the sine, being an odd function, will change sign. So we get and this will be the inverse matrix. And as before, you can check that A times the inverse is equal to the inverse times A, which is equal to the identity matrix. In order to do this, you will have to use the trigonometric identities. Cosine squared plus sine squared equals 1. So these are two very simple examples of an inverse transformation and the inverse matrix. Thanks for watching.